In my last lecture, I discussed various problems pertaining to the applications of Maxwell's relation. Also, in my previous lecture, I derived the Clausius-Clapeyron equation as an application of Maxwell's relation. Therein, I had also told that we can derive the Clausius-Clapeyron equation by considering the Gibbs free energy. So this is what we will do in today's lecture. We will discuss the phase transitions, both of the first order and the second order. The phase transition of the first order gives us the Clausius-Clapeyron equation, and the phase transitions of the second order gives us the Ehrenfest equations. At the end of this lecture, you will appreciate the difference between the first order and the second order. So first of all, what is meant by phase transitions? Phase transitions is a process of change of state of matter. Phase transitions can be of the first order and can be of the second order. So let us first discuss the first order phase transitions. First order phase transitions are the phase changes when a solid changes to the liquid state, or liquid changes to the vapor state, or the vapor state to the solid state. That is, the processes of melting, vaporization and sublimation signify the phase transitions of the first order. A first order phase transition is the one in which a system absorbs heat or releases heat without any change in pressure or temperature, but the entropy and the volume of the system changes. So pressure remains a constant, temperature remains a constant, but entropy and the volume can change. Examples being the constant temperature at which change of state from solid to liquid occurs is called the melting point. Similarly, from liquid to vapor state is called the boiling point, and from solid to the vapor state is called the sublimation. The heat energy alone cannot produce both a change of state and a change in temperature simultaneously. The specific latent heat of fusion is the heat energy required to change the unit mass of a substance from the solid to the liquid state at its melting point. In the case of water, the latent heat of fusion is 3.35 into 10 to the power 5 joules per kg. The specific latent heat of vaporization is the quantity of heat required to change the unit mass of a substance from the liquid to the vapor state without a change in temperature, that is at the boiling point. LV is 2.26 into 10 to the power 6 joules per kg. Now, this figure is showing the variation of temperature of ice with heat energy when it is heated. On the y-axis, we have temperature. On the x-axis, we have heat energy. If initially we have ice form of water, then when heat is applied, the temperature increases from -25 to 0. At 0 degrees, melting takes place because of the latent heat of fusion. Then from 0 to 100 the water is heated. At 100 again water changes into steam because of the latent heat of vaporization. Let us now discuss what are the characteristics of the first order phase transitions. As mentioned before, during this kind of phase transition, the pressure and temperature remains a constant and both entropy and volume undergoes some kind of change. Second very important characteristic, the Gibbs energy remains a constant in both the phases, but the first derivative of Gibbs energy with respect to pressure and temperature is discontinuous at the transition point, that is the point at which the phase change is occurring. I will be showing you the figures, the graphs shortly to make this point even clearer. Now we know that the Gibbs function is defined as H minus Ts, or G can be written as F plus PV. H is the enthalpy, F is the Helmholtz free energy. For an infinitesimal reversible process, the above equations can be written as dG is equal to dH minus TdS minus SdT, or dH is equal to TdS plus VdP. Hence, dG can be written as TdS plus VdP minus TdS minus SdT. TdS gets cancelled on the right hand side, so we are left with dG is equal to VdP minus SdT. In my previous lecture, I had told you that this equation shows that the natural variables for Gibbs free energy are pressure and temperature. At constant temperature, we have dT equal to 0. Thus, delta G by delta P at constant temperature is equal to volume, and at constant pressure, dP is equal to 0. Thus, delta G by delta T at constant pressure is equal to minus entropy. The above equation is called fourth, and this is called equation 3. From the TdS equation, we have TdS is equal to Cp dt minus T times delta V by delta T at constant pressure into dP. Now, since we are considering an isobaric process, dP is equal to 0, and the above equation becomes TdS is equal to Cp dt, or Cp is equal to T times delta S by delta T at constant pressure. Call this equation 4, and equation 4 is well known and has been used before in the lectures also. Now, this figure is showing the variation of Gibbs energy, the variation of volume, the variation of entropy, and the variation of heat capacity with temperature. You can see that the Gibbs function varies continuously across the phase transition point. Entropy has a discontinuity at the phase transition point. Volume again has a discontinuity. Now let us show that the Gibbs function is a constant during the first order phase transition. Consider a system of liquid and vapor in equilibrium state. We have seen that the first order phase transition is characterized by constant temperature and pressure in both the phases. Thus, the product of specific values of functions u, s, v and g and their masses are equal to the thermodynamical coordinates. Let small g1 and small g2 be the Gibbs function of the two phases, that is the liquid phase and the vapor phase, m1 being the mass in the liquid phase and m2 being the mass in the vapor phase. Then we have capital G is equal to m1 into g1 plus m2 into g2. Call this expression 1. G, remember, is the Gibbs potential of the whole system. G1 is the Gibbs potential, specific Gibbs potential of one phase. Both the phases combined make the whole system. If a small quantity of liquid changes to vapor, then differentiating the above equation, we get dG is equal to delta m1 g1 plus delta m2 g2. As this process takes place at constant temperature and pressure, that is under isothermal and isobaric condition, the Gibbs potential does not change, that is dG is equal to 0. This is because temperature and pressure are the natural variables of the Gibbs potential, and just a few slides back I had shown this particular property of the Gibbs potential. So we now are left with dG is equal to 0. The above equation would then become 0 is equal to delta m1 g1 plus delta m2 g2, or delta m1 g1 is equal to minus of delta m2 g2. In a closed system, the gain in the mass of vapor delta m2 will be equal to the loss in the mass of liquid delta m1. Why? Because the gain in one is going to be reflected by the decrease or the loss in the other. So we have delta m1 is equal to minus delta m2. Negative sign means loss. Gain of one means loss of the other. So we have put a negative sign here. Thus we get G1 is equal to G2, that is, the value of the Gibbs function in the two phases are equal. This is a very important property of the phase transition of the first order. Now, on the basis of what we have studied up till now, let us derive the Clausius-Clapeyron equation for the first order phase transition. To derive this equation, consider an enclosed system of liquid with its saturated vapor in equilibrium. As the system is undergoing isothermal and isobaric change, the Gibbs potential is a constant during the phase change, as we have just seen. That is, G1 is equal to G2. Call this equation 1. Now, let us change the temperature from T to T plus dt and the pressure from P to P plus dP. Then, for equilibrium conditions, we have G1 plus dG1 is equal to G2 plus dG2. Using the condition 1 in equation 2, we get dG1 is equal to dG2. If the condition of saturation is satisfied, then because dG1 is equal to d2, it follows that dG1 by dt saturated condition is equal to dG2 by dt under saturated conditions. Call this expression 3. As the pressure is also changing from P to dP, we can write dG is equal to delta G by delta T at constant pressure dt plus delta G by delta P at constant temperature dP. Let us divide the whole equation by T. We then get delta G by delta T is equal to delta G by delta T at constant pressure plus delta G by delta P at constant temperature into delta P by delta T. Call this equation fourth. Now, we have just seen in a few slides back that the change in Gibbs function is given by dG is equal to VdP minus SdT. From this equation, it follows that delta G by delta P at constant temperature is equal to volume, and delta G by delta T at constant pressure is equal to minus S. S is the entropy, small g is the specific value of Gibbs function, capital G is the Gibbs function of the entire system. Putting these values in equation fourth, we get delta G by delta T under saturated condition is equal to minus S plus V into delta P by delta T. The above equation for the two phases can be written as d delta G1 by delta T under saturated condition is equal to minus S1 plus V1 into delta P by delta T. Here we have taken the subscript 1 to differentiate between the two phases, phase 1 and phase 2. Phase 1 can be liquid phase, phase 2 can be gaseous phase, or so on so forth. For the second phase, we would then have delta G2 by delta T under saturated condition is equal to minus S2 plus V2 into delta P by delta T. By substituting the above equations in 3, we get minus S1 plus V1 delta P by delta T is equal to minus S2 plus V2 into delta P by delta T. Rearranging this equation, we get on the left hand side delta P by delta T, and on the right hand side we get a ratio of two terms S2 minus S1 and V2 minus V1. Call this equation 5. Now remember, the amount of heat absorbed dQ is defined as Tds. ds is nothing but S2 minus S1. So what do we get? We get S2 minus S1 is equal to dQ by T. Further, as the phase is changing at constant temperature and L denotes the latent heat and M denotes the mass of the system, then dQ can be written as M into L. Using this fact, we can write S2 minus S1 is equal to ml by T. If M is equal to 1, then S2 minus S1 is equal to L by T. By substituting for change of entropy from 6 to 5, we get dP by dt is equal to L by T V2 minus V1. This equation is called Clausius-Clapeyron equation. If M is not equal to 1, then we would be having ml by T V2 minus V1, and as done before, the M occurring in the numerator is taken in the denominator such that we get V2 by M and V1 by M, which represents the specific volumes. Now let us discuss the applications of Clausius-Clapeyron equation. The first is the effect of pressure on the boiling point of liquids. When a liquid changes its state to vapor state, its volume increases, that is, V2 is greater than V1, or V2 minus V1 is a positive quantity. From Clausius-Clapeyron equation, we have dP by dt is equal to L by T V2 minus V1. Since in the denominator V2 minus V1 is positive, it follows that the left hand side, that is the dP by dt, is also positive. So what can we infer? We can infer that as the pressure is increased, the boiling point also increases. In case of water, it boils at a temperature greater than 100 degrees Celsius if the pressure is increased beyond 1 atmosphere. This particular phenomena or this particular property, which is a natural occurrence of the Clausius-Clapeyron equation, explains why food gets cooked faster in a pressure cooker. Next, let us consider the effect of pressure on the melting point of solids. When a solid changes its state to liquid state, its volume increases. That is, V2 is greater than V1, which would also mean that V2 minus V1 is a positive quantity. So we get dP by dt is equal to L by T V2 minus V1, or dP by dt is also a positive quantity. Thus, as the pressure is increased, the melting point also increases. For example, wax and sulfur. In case of ice, gallium and bismuth, V2 is less than V1. So we get V2 minus V1 is a negative quantity, which would give me that dP by dt is a negative quantity. This means that for these substances, as the pressure is increased, the melting point decreases. In case of ice, whose melting point is 0 degrees at 1 atmosphere, it will be less than this value at higher pressures. So this is a very nice illustration of the Clausius-Clapeyron equation. Another illustration of the Clausius-Clapeyron equation is the triple point of water. The triple point of a substance is the temperature and pressure at which the three phases, gas, liquid and solid, of that substance may coexist in thermodynamic equilibrium. I have discussed about the triple point in my last lecture also, and in the subsequent lectures I will again take up this topic along with solving a few problems based on the Clausius-Clapeyron equation and discussing what is the phase transition of the second order. I hope you have understood today's lecture. Thank you.